Okay, let's do this problem piece by piece. First, they want us to find the domain of this function, and we can do that since this function has a denominator by saying that that denominator cannot equal 0. That is our domain, we just have to write it in interval notation. So if you think about a number line with the x value 0 missing from it, that number line is split into two pieces, one piece from -infinity to 0, and the other piece from 0 to infinity, and that is the domain of this function. Here we go, that's the domain of the function. Okay, now to find x-intercepts of a function, what that means is you're going to set y equal to 0. I have that note right up here. To find the x-intercept of any function, we're going to set y equal to 0. What that means in this case is we're going to set f of x equal to 0. And essentially what that means when we're talking about rational functions is we're setting the numerator of our rational function equal to 0. Because the only way for a fraction or a rational function to equal 0 is if its numerator equals 0. Another way to think of that is we can take this equation and multiply both sides of the equation by x, but 0 times x just gives you 0, and the right-hand side is going to give us 5. So we have 0 equals 5. That is not a true statement, obviously, which actually just means we don't have any x-intercepts for this function. Okay, now we want to find the y-intercepts of this function, and I have a note up here that says to find the y-intercepts of any function, we just set x equal to 0. Well, what's going to happen if we set x equal to 0 in this function? The appropriate notation would be f of 0, and then we have a 0 in the denominator. That is undefined. That tells us that we have no y-intercepts. Okay, what's the next question? Let's find the vertical asymptotes. Now, previously, we spent a little bit of time finding vertical asymptotes, and these are our notes for finding all asymptotes. To find a vertical asymptote, after factoring and simplifying, you just set the denominator equal to 0. So our denominator in this case is pretty simple, it's just x. So we're just going to say x equals 0, and that is our vertical asymptote. So I'm just going to go with it, x equals 0, that is it. What else do they want to know? Find our horizontal asymptotes. Check out our notes for horizontal asymptotes, and notice that the degree of the denominator is 1, while the degree of the numerator is actually 0. So the degree of the denominator is bigger. That means that we're going to have a horizontal asymptote, and that equation of that horizontal asymptote is simply y equals 0. Okay, what else? They're looking for oblique asymptotes. Now the only way, again, to get an oblique asymptote is if the degree of the numerator is 1 bigger than the degree of the denominator. That is not the case here because our degree of our denominator is bigger. So we have no oblique asymptotes. Okay, let's take a look at another one. I'm going to let you graph these things on your own. Use Desmos, use whatever graphing tool you want, use your TI-83. I'm going to move on to the next problem. Okay, so here is another function, and we're going to do all of the same steps. Let's start by finding the domain of this function. Okay, so to find the domain of a function, probably the best thing to do would be to factor first. We can factor an x out of the denominator, and before we do any simplification, we should find our domain. So our function is rational, it has a denominator, so we're going to say that this whole thing cannot equal 0. Before we do any simplification on this thing, we can split this thing into two pieces. One piece says that then x cannot equal 0, and the other piece then says x cannot equal -4. Now, if you drew out a pretty crappy number line here, right here would be x equals -4, and right here would be x equals 0. Your domain is all other x values. Everything over here is fair game as an x value to plug into this original function. Everything in between -4 and 0, and everything to the right of 0. All of those x values are okay to plug into this function. However, we cannot plug x equals -4 or x equals 0 into the function. So that actually splits our domain into 3 pieces, as you can see from this number line. One piece goes from -infinity to -4. The next piece goes from -4 to 0. And the final piece goes from 0 to infinity. And that is the domain. I'm going to take a little bit of time and type this in. Okay, so how about x-intercepts? Well, our notes right up here, again, said that to find x-intercepts, we set y equal to 0, or we, after simplifying, just set the numerator equal to 0. Well, if we simplify this thing, and we should, let's write down what happens when we cancel the factor of x from both the numerator and the denominator, we get 1 over x plus 4. So if we're trying to find the x-intercepts of this function, what we do is we take that numerator, in this case again it's just 1, and we set it equal to 0. Again, this is not a true statement, so this just means that we have no x-intercepts. Okay, let's go on to the next piece. So to find our y-intercept, we're going to set x equal to 0, as we always do, and we're going to have to plug that into the original function. The original function here had an x in the numerator, so that becomes 0. In the denominator, we had an x squared and a 4 times an x, and if you simplify this, you notice pretty quickly that you get 0 over 0. Later when you take a calculus class, you might call that an indeterminate form, but we're just going to say since the denominator is 0, this does not exist, and therefore there is no y-intercept for this function. Now, as far as vertical asymptotes are concerned, what we do is we simplify first, and then we look at our denominator. Our denominator is x plus 4. If we set that equal to 0 and subtract 4 from both sides, we're going to get a vertical asymptote of x equals negative 4. That is our answer. If we're talking about horizontal asymptotes, what we do is we go back to our notes and we look and we see, okay, so our degree of our denominator is bigger than the degree of the numerator. That gives us a horizontal asymptote, and the equation for that horizontal asymptote is y equals 0. Okay, and as far as an oblique asymptote goes, that is not going to happen because the degree of our denominator is bigger than that of the numerator. For an oblique asymptote, the degree of the numerator has to be 1 bigger than that of the denominator, so there is no oblique asymptote, and we can call this problem finished. Go ahead and graph that thing using your favorite graphing utility and match it up with the picture. One thing that I should point out is that when we canceled this factor from the numerator and the denominator, it created a hole in the graph. And since we canceled just an x out of the numerator and the denominator, that hole is actually going to occur just at x equals 0. So you're going to see in each one of these pictures below that there's actually a little hole right in the graph at x equals 0. Your favorite graphing utility might not actually show that depending on which one you use, but that's why that hole is there. And let's take a look at the next problem. All right, I'm going to let you do these problems on your own because it's pretty similar to the last one that we did. There might be some mild complications. Let's do problem 14 together. It is usually a good idea to factor if you can, and if you factor that numerator and factor the denominator, you'll notice that we are going to get some cancellations. That term is going to cancel, and we're going to end up with an x minus 1 in the numerator and an x plus 2 in the denominator. Okay, but first we need to find the domain of this function. Well, the domain of a function should be found before we make any cancellations. So we're going to take this denominator right here for our domain and say denominators cannot equal 0. So this first factor tells us that x cannot equal negative 3, and this second factor tells us that x cannot equal negative 2. That is going to be our domain. So we could draw a little picture. This is negative 3 on our number line and negative 2 on our number line. You'll notice that these two holes in our number line split the number line into 3 pieces. One piece on the far left goes from negative infinity to negative 3. Our next piece on the number line goes from negative 3 to negative 2. And our last piece on the number line goes from negative 2 to infinity, and that should be our domain. Next question, we want to find x-intercepts. Okay, so after simplifying, we can find our x-intercepts by setting the numerator of this thing equal to 0. So the numerator we're going to take is this x minus 1. We're going to set it equal to 0. That gives us an x-intercept of x equals 1. We actually have to make a point out of that because intercepts are technically points. The x value of this point is 1, and the y value of every x-intercept is always going to be 0. That's where this graph crosses the x-axis, so its y value is 0. All right, next problem, y-intercepts. We're going to find y-intercepts by setting x equals to 0. And I pluralized intercepts, but we should only have one at most y-intercept for each graph. Anyway, we're going to plug x equals 0 into our function. You can plug x equals 0 in this example into several places, but if we go back to the very first function and we find f of 0, you'll notice that the numerator turns into a 0 plus a 0 minus a 3, and the denominator turns into a 0 plus a 0 plus a 6. That simplifies to negative 3 over 6, which is negative 1/2. So our y-intercept is going to be x equals 0, y equals negative 1/2. As far as vertical asymptotes are concerned, what we can do is we can look at our simplified version of our function, look at the denominator. The denominator is x plus 2, so that's going to give us a vertical asymptote of x equals -2. As far as horizontal asymptotes are concerned, we finally get to use the other rule for horizontal asymptotes. If I scroll all the way back up to our notes at the beginning of this section, if the degrees of the numerator and the denominator are the same, we have some horizontal asymptote, and it's a over b. But what is that a over b? Well, as it turns out, that a over b is the leading coefficient of the numerator, that would be a 1 in this example, divided by the leading coefficient of the denominator. That's another 1, for example. So our horizontal asymptote is going to be y equals 1 over 1. And you probably shouldn't type it in as 1 over 1 because 1 over 1 simplifies to just 1. So that is our horizontal asymptote in this case. Again, we had to use a slightly different rule there because the degree of our numerator and the denominator are the same. As far as an oblique asymptote goes, we will not have one. We'll never have a horizontal and an oblique asymptote at the same time. Okay, so that does it for that problem. I'm going to have you graph that thing on your own using your favorite graphing utility. I'm going to scroll through these and just take a look and make sure there's nothing else that you'll need help with. Let's do this last problem. This is problem 16. So we have a function, and it gives the body concentration in parts per million of a certain dosage of medication after t hours. And the question is, what is going to happen as t gets really, really big? So maybe one way to investigate this is to graph this thing. So I'm going to spend a minute in the background graphing this function. I'm just going to bring up maybe Desmos. And Desmos likes it when we use x values instead of t values. So I'm going to ask Desmos to graph this thing. I'm going to make this bigger. And if I zoom out, you'll notice that this thing has some asymptotes. Now, the only part of this graph that we really care about is when t is positive, because that means time is running forwards. And the question that this problem is asking is, what happens to this red line as our t value, or our x value as I put it in, goes to infinity? So what happens to this graph as time goes on? Well, we could zoom in on this thing, but what we're going to find is that this function actually has a horizontal asymptote over here. And that horizontal asymptote tells us what happens to the graph of this function as x gets really, really big, or as x goes to infinity, as we say. To answer this question, what we need to do is we need to find the horizontal asymptote of this function. And you'll notice that the degree of the numerator and the degree of the denominator are the same. So we're going to use that rule that says that we're going to take the leading coefficient of the numerator and divide it by the leading coefficient of the denominator, and that is going to be our horizontal asymptote. Now 0.8 divided by 6 is approximately 0.13, and you can see that that is one of our options right here. So what does that mean? Well, whatever drug this is, when it gets into your body, as time goes to infinity, meaning as several days, months, and years go by, the concentration of that drug in your body is never going to go below 0.13. In other words, that concentration never decreases to 0. So okay, I think that's going to do it for 4.5. Let's move on to section 4.6 in the next video.